Good afternoon. Hi, good afternoon, everyone. My name is Haefa Mansour. I'm a graduate student in the Enrique Iglesias group at UC Berkeley. And today I'll be talking about the mechanism of hydrogen oxidation on platinum clusters and its consequences for selectivity and the oxidation of mixtures of hydrogen and hydrocarbon. The motivation behind this work stems from one of the main challenges associated with dehydrogenation reactions, and that is their inherent thermodynamic constraints. Here we show for isobutane dehydrogenation in a batch reactor, the product isobutene quickly levels off at fairly low conversions due to the equilibrium limitations. At the same time, hydrogenolysis is a more thermodynamically favorable reaction, and so the selectivity decreases as the conversion increases. We can write the net rate of dehydrogenation as the forward rate times 1 minus the approach to equilibrium, which is the ratio of products to reactants raised to their respective stoichiometric coefficients and divided by the equilibrium constant. And because hydrogen as a product appears in the numerator of this reverse rate of reaction, if we can reduce the concentration of hydrogen or eliminate it entirely, we can eliminate this reverse rate of reaction. We do so via scavenging the hydrogen via reaction with oxygen, doing hydrogen oxidation, which is a very exergonic reaction. But the main problem with this approach is that the alkanes and alkenes can combust as well to form CO and CO2. Now, we define a selectivity parameter chi as the ratio of oxygen consumed via hydrogen oxidation to that consumed via hydrocarbon oxidation. And looking at this reaction on noble metal catalysts, we see that platinum and palladium are remarkably selective for this reaction, with selectivity parameters of about 100 at these conditions. And so the objective of this part of the project is to understand why platinum is so selective for hydrogen oxidation. And this involves identifying the mechanism by which hydrogen oxidation proceeds on platinum and using density functional theory calculations to verify our proposed mechanism and probe some of the surface non-idealities that play a large role. This is an extremely fast and exothermic reaction, and so extensive dilution at the scale of the pellet and the bed is required in order to eliminate these heat and mass transport effects. So we use intraparticle dilution ratios above 800 and bed dilution ratios above 20,000. And in doing so, at these dilution ratios, the rates become independent of dilution ratio and the platinum loading. So all of these rates that we'll be reporting are of intrinsic chemical origins. So looking at the kinetics of hydrogen oxidation, we report oxidation turnover rates, that is moles of oxygen per surface platinum per second. And we see that they're proportional to oxygen pressure, which tells us that there are 2 oxygen atoms involved in the transition states of the kinetically relevant step. And this is true across all the hydrogen pressures that we've used here. And when we look at the rates and the dependence on hydrogen pressure, we see that it initially decreases with respect to hydrogen pressure, but ultimately becomes independent of hydrogen pressure, which indicates that our most abundant surface intermediate is hydrogen-derived. The most likely candidate for this intermediate would be an adsorbed hydrogen atom. And if we look at hydrogen hemisorption isotherms measured at reaction temperatures, we see that hydrogen coverages are significant at these relevant temperatures. But in order to determine whether we can use these isotherms to describe the data, we need to determine whether our surface hydrogen coverages are in equilibrium with the gas phase. We do this by looking at hydrogen-deuterium isotopic exchange and measuring the rates of HD formation, which tells us something about the total recombinative desorption rate. And when we look at the ratio of the total recombinative desorption rate to the oxidation rate, we see that it's greater than 8 times at all the conditions reported here, which indicates that we are quasi-equilibrated. And so we can use the hydrogen chemisorption isotherms in order to rigorously determine what the coverages are at the relevant catalytic conditions. Now, it seems surprising that our surface is covered by hydrogen when we know that platinum oxygen binding energies are much stronger than that of hydrogen. But oxygen is not in equilibrium, the surface oxygen is not in equilibrium with the gas phase oxygen pressures, and the oxygen is set by the pseudo-steady state between its dissociation on the surface and the fast scavenging via reaction with hydrogen. So looking at this first regime here, this first pathway involves hydrogen in the denominator, but because we're negative first order, that means that there are no hydrogen-derived species that are appearing in the numerator. And so this elementary step could only be the reaction of gas phase oxygen or molecularly absorbed oxygen with vacancies on the surface. And so the most likely step describing this would be dissociation of oxygen on the surface, which we denote as K star star. Now, if this were the only kinetically relevant pathway, we would expect the rates to continue to decrease with oxygen pressure and ultimately approach zero. But instead, because we approach this zero order regime, that indicates that there's a second kinetically relevant pathway that involves a hydrogen term in the numerator. This pathway must involve 2 hydrogen atoms, and so the possibilities here are the reaction of 2 surface hydroxyls or the reaction of gas phase oxygen with hydrogen atoms on the surface to form reactive intermediate hydrogen peroxide. We can eliminate this first possibility because it would require the reversibility of oxygen activation steps. And so we're left with this reaction of oxygen with the surface in order to form hydrogen peroxide, which quickly decomposes in steps that are fast and not kinetically relevant. And we denote this step with a rate constant K H star H star. Okay, so we have a rate equation that involves 3 parameters, one of which we can measure independently. That's the dissociative hydrogen absorption constant. And we do this for 2 main reasons. The first is that it lends greater credence to the fit that we get for the other 2 parameters and avoids the possibility of cross-correlations at these significant hydrogen coverages. And the second is that the equilibrium dissociative absorption constant is actually a function of coverage. So we can use data from the hydrogen chemisorption isotherms in order to determine these fractional coverages of surface vacancies and the hydrogen atoms. And we only have 2 parameters here. Now, we want to evaluate the plausibility of these steps, and so we would like to measure activation enthalpies and entropies for these steps. So we can measure these reaction rates at various temperatures and regress the data to this functional form of the rate equation in order to extract the 2 rate constants. And when we do so, we're able to obtain the activation entropies and enthalpies. These activation enthalpies for each pathway are somewhat similar, but the activation entropies differ by about 20 kilojoules per mole. And when we think about what an activation entropy would mean for this step, both of these pathways involve bringing a gas phase oxygen molecule to the surface in a substantial loss in translational entropy, which we can estimate as being about 100 joules per mole Kelvin from statistical mechanics treatment. But then additionally for the second pathway, which has a greater loss in entropy, there's an entropic penalty for the partial loss in mobility of the hydrogen atoms on the surface. These hydrogen atoms are mobile at these temperatures and can be modeled as an ideal gas. Now we measure a rather weak kinetic isotope effect for this parameter, which is the ratio of this constant using hydrogen versus using deuterium. So this indicates that we have a very early transition state. And moving on, looking at the DFT, we will verify So looking at this pathway with DFT, we model this reaction on a platinum 111 plane because it's the most prevalent facet on platinum clusters of this size. And we put our hydrogen adsorbates. We can use 3 different binding modes. We start with the most stable binding mode with threefold FCC position. And when we bring in an oxygen molecule from the gas phase and do a NEB and dimer calculation, we find barriers of about 20 kilojoules per mole, which is pretty similar to what we measure from the experiment. This transition state is very early, as indicated from the fact that the oxygen-oxygen bond length barely changes between the reactants and the transition state. And the kinetic isotope effect that we calculate using vibrational frequency calculations is approximately the same as what we measure experimentally. We do the same thing for the threefold HCP position, and we obtain similar barriers. And for the atop position of the hydrogen, we obtain a substantially lower barrier. Again, still a very early transition state, as indicated from the lack of one thing. Now moving on to the oxygen dissociation pathway. So this occurs on vicinal vacancies on the surface. And so we use a bare platinum 111 plane as our precursor. And we actually find that the barrier for dissociation is, with respect to the gas phase oxygen, there actually is no barrier. And so this was a little bit surprising. But then we considered that we needed to add the hydrogen co-adsorbates in because they have repulsive interactions. And so what we did instead was we placed our hydrogen atoms on the surface and then removed 2 of them in order to represent 2 vicinal vacancies that we assumed that this reaction occurs on. And when we do this, we obtain very substantial barrier. And this is 72 kilojoules per mole. So we can look at the dissociation barrier for oxygen as a function of what we call the platinum ensemble size, or the number of adjacent vacancies. And we see that this has a very substantial effect, regardless of whether we put the hydrogen in the atop position or in the threefold FCC position. And so this means that we can't really use a single rate constant to describe this reaction, but rather we would need to ensemble average over all of the transition states present in order to rigorously determine what these rates would be. And so this average barrier that we're measuring, 31 kilojoules per mole, reflects that ensemble average. Okay, so moving forward to what we've seen so far is that there are two oxygen activation pathways for this reaction. The first involving dissociation on vicinal vacancies, and the second involving direct reaction with adsorbed hydrogen atoms. But what happens when we add another reductant to the mix? So how does that affect the relative rates of each of these pathways? So when we add a hydrocarbon, we're adding another term to the denominator here, another abundant surface intermediate, and decreasing the fractional coverage of surface vacancies, making this secondary pathway more relevant. Now, what does this mean for hydrocarbon oxidation? Previous work has shown that hydrocarbon oxidation requires adsorbed oxygen atoms on the surface that are formed via oxygen dissociation, and that the hydrocarbon is not able to undergo this secondary pathway for the reaction, which involves reacting oxygen with the surface directly. So to summarize, we've shown that hydrogen oxidation involves 2 oxygen activation pathways, the dissociation on bare platinum sites and the reaction with adsorbed hydrogen atoms on the surface. We've shown that these relative reactivities are driven by differences in the entropies, activation entropies, as well as the fractional hydrogen coverages. And we've shown that these high hydrogen oxidation selectivities reflect the ability of hydrogen atoms to react directly with oxygen molecules from the gas phase, in a single surface sojourn, but the fact that the hydrocarbon-derived intermediates are not able to undergo this route. I would like to acknowledge my funding sources, the Berkeley Graduate Fellowship Program, the NSF Graduate Fellowship Program, and BP. And then, of course, my research group, LSAC, and Dr. David Hibbets for developing the framework with which we run these DSP calculations. Thanks.
Questions for Haefa?
Hi, nice talk. Have you considered the possibility that oxygen could be reduced to a hydroperoxy intermediate that could be facilitating this chemistry as well? It's commonly reported in electric catalysis literature, for example, that most oxygen dissociation occurs through a hydroperoxy intermediate.
Yeah, so that was actually the first route that we tried with Dept. And in this case, the hydrogen peroxide formation is so much more favorable. Although the transition states of some of them looks almost like a hydroperoxyl intermediate. So for the case of the hydrogen in the threefold binding location, you could even think of it as being occurring one hydrogen transfer at a time.
More questions? Could you explain what you mean by the ensemble averaging? Is it the number of platinum atoms that don't have hydrogen, or
yeah? So we define a platinum ensemble as basically the number of bare platinum sites, and because that dissociation barrier depends on the number of these bare sites. And so ultimately, when we're doing this oxygen dissociation or measuring a rate, the barriers change as a function of all of these sites, and so if we were to do this rigorously, we would need to average over each of these possibilities and the prevalent coverages on the surface.
Yeah, but in general, you're in a hydrogen-covered condition, right? So how does the probability of forming those ensembles going to?
Yeah, so at these conditions, at these pressures, the hydrogen coverages range from about 0.7 to 1. So there are, I guess, still vacancies in these groups.
Thank you for a nice talk. So I have a question. You show that hydrogen is polycoupled on atom surface, right? Then how it affects the deoxygenation reactions that you care about from the butane or butene? So the original reactions, will this affect the activities? Reactions have?
So when you add the hydrocarbon there, if you're adding an additional reductant, then you're further decreasing the concentration of oxygen on the surface and the concentration of vacancies on the surface. As far as, I'm not sure if you're referring to the dehydrogenation part of it, or?
Yeah.
Yeah, so because this is not oxidative dehydrogenation, these are occurring actually on two separate catalyst phases. The dehydrogenation would occur in sort of one component, and then the effluent of that reactor would be fed to this catalyst bed, which is intended to only do selective hydrogen oxidation. So we haven't, for this part of the project, looked at the effects of the oxygen on the dehydrogenation reaction.
Questions? If there are no more questions, let's thank the speaker again.